Hello and welcome to this session on current electricity. I have divided this topic into two sections, part 1 and part 2. So we deal with part 1 today and learn some basics of current electricity. Well, what is current? Electric current more specifically. Basically, electric current is nothing but flow of electric charges, much similar to a water flow. Okay, we'll come to this analogy a little later. Basically, electric current, when I say it is flow of electric charges, when it flows when there is a potential difference. Well, get back to our basics of electrostatics. We have studied in electrostatics that there are two kinds of charges: positive charge and negative charge. When two opposite charges or unlike charges come together, they attract. When like charges come together, they actually repel. So there we have force of attraction and repulsion. So, and this electric charge is basically contributing to the electric current when they flow in a conducting medium. When I say when they flow, it means that they can flow only when there exists a potential difference. Now, again in electrostatics, we have studied something called electric potential and potential difference. It is possible for charges to be separated by some potential, and there exists a high potential and a low potential. When there is such potential difference, the charges start flowing, which we call electric current. Much similar, as I said, to a water flow. Water can flow from a high pressure area to a low pressure area. When water is at the same level, for example, I have shown here two beakers filled with water to the same level. When they are filled to the same level and there is a connecting pipe between them, we don't see the water flow because they are obviously at the same level. Same thing applies to an electric current. When there is no potential difference, that is, there is no high and low, they are both equipotential, same potential, there is no current flow. So current flows when there is a potential difference. Let's get to that point. We have not just now seen that electric charges are the basis for current flow. So where do we get these charges from? Well, we have electrochemical cells and we have conductors. Okay, so these are materials which has charges present in it. One such conductor we all know is copper. Now what does a copper has? If you get into the atomic structure of a copper, this is how the electrons are distributed surrounding the nucleus. And in the outermost shell, we have one free electron. This is the nature of a copper atomic structure is. And this free electron is loosely held to the parent atom and therefore can be easily be dislodged by pumping in little bit of energy. When this electron starts dislodging from its parent atom, we see the current happening. Well, now we have a wire of conductor, copper conductor, and we know that there are a lot of charges present in it, and there are electrons which are attached to the atom. Now, as such, as a bare wire cannot contribute to electric current. What we need to do is that extra energy, the pumping energy, as I said, for dislodging this free electron. So that is being provided by a cell here. The cell excites the electrons. Let's consider one electron which is now kicked out of its parent atom, which comes out to the external wire. Now here it makes a vacancy which gets filled by the neighboring electron. When the electron moves and fills the vacancy created by the previous electron, there is one more vacancy created at this place, and another adjacent electron is able to occupy it. So it's a continuous process wherein electrons start drifting and they move towards the positive terminal of the battery or the cell. Why? Because this is positive, and therefore electrons get attracted to the positive terminal of the battery and they move like this. And the electrons are also, whatever the deficit in the conductor because of the movement of the electrons, the net deficit is being supplied by the cell to replace those electrons. So therefore there is continuous flow of the electrons, and this constitutes electric current in any conducting wire or a conducting medium. This is all the basics of current flow is. One important note here is about the direction of the current. You have seen that the electrons actually are the reason why there is an electric current. But since ages, it has been followed that current flows from positive terminal to the negative terminal of the battery. That is called conventional current, which is against the electrons flow. There is a story or history towards that reason why current is considered to be from plus side of the cell to the minus side of the cell. We'll not dig deep into it. There is a history to it, starting from Benjamin Franklin to Rutherford. It is an accepted fact that now current direction is always from positive to negative, though we understand the underlying reason is the electrons. Coming to what is current is all about. Now how much of current is flowing in a wire? Now we know that current flow is happening. Now how much current is flowing through the wire? That is what is called strength of a current. We can measure the current across a conductor by cutting across the cross-sectional area of the conductor and then finding how much of charges are flowing in 1 second. Okay, much similar to a pipe, a water pipe, and I have a flow meter. Okay, a water pipe, and if I want to know how much of water is flowing, all that I need to do is fix a flow meter across this cross-sectional area of the pipe, and then my flow meter will indicate in 1 second how much of water is flowing. Similar to that, I can fix a current meter here to measure the amount of current or the strength of the current. That brings us to find what is the unit of current. The unit is ampere, and then 1 ampere, just give me a second. So 1 ampere corresponds to 1 coulomb of charge flowing in 1 second. So that's massive, right? So 1 ampere is defined as 1 coulomb of charge flowing in 1 second, and I just discussed how that measurement can be done. And this can be equated in another way, in generic way, I, which is symbolically representing current, and Q being the charge, and T the time. So I is Q by T, is the rate of flow of charge. Okay, that is your current strength. Well, just what we discussed is about the strength of current flow in a conductor. Now we just discuss about what is a circuit is. A circuit basically is a continuous conducting path between the positive and negative terminals of a cell, or could be another source. So the source which pumps in the necessary power is basically provides the excitation for the current flow, and the path which is continuously providing the way for current to flow is called an electric circuit. In this diagram, I have depicted two circuits. One is an open circuit, another is a closed circuit. What do I mean by that? Well, I have a switch here. So when the switch is open, it's an open circuit. Mean to say, though there is a power source here, the current cannot find a continuous path to flow. There is a break in the circuit, and therefore no current can flow. In this diagram, I have shown you the case for closed circuit, where the switch is closed. In this case, current starts flowing from the source, and it finds a closed path, and it is continuous too. So the current keeps on flowing in this circuit, which is called as closed circuit. Well, these are the basics. Let's now discuss about something called resistance. Okay, we all know that by nature there is always opposition to the current flow. So when there is a current flow, there is always a resistance within the conductor against the flow of charges, which we call it as resistance. So we'll say resistance, symbolically represented by R, capital R. Electrical resistance is that property of any conductor which opposes the current flow. Again, we can draw the analogy to water flow, where the friction in the pipe is nothing but the resistance to the water flow. So therefore, in a conductor, the resistance is a property of the material to oppose the current flow. Now we have come close to one more concept about the current flowing in a conductor, and there is a resistance of that conductor. And now what happens when you connect a battery or a cell to this conducting wire, and it has some resistance? This is a circuit symbol for a resistance. Okay, it can be drawn like this, R. Well, after closing the switch, we now understand that current flows in this circuit. As the current flows, there is a resistance. Okay, so you have a voltmeter which measures the potential difference across this resistance, and then ammeter which measures the current flowing in the circuit. It was observed by George Simon Ohm that this current kept on increasing. Okay, so kept on increasing as the number of cells were increased. This is called, this connection which we eventually discussed in part 2 is called series connection. Okay, in series connection, if this is 1.5 volt and this is another 1.5 volt, the net voltage now is 3 volt, and as you increase the number of cells in series, the voltage gets added up, and therefore George Simon saw in his experiment the current also raised, which I show here graphically, current raising as the voltage increases. So this, he put it in his law, stating that the current flow in a conductor, may I rub this with permission, so I need to depict something here. The current flow in a conductor is directly proportional to the potential difference applied to the conductor. The current flow is directly proportional to the potential difference, which means the cell in this case, applied to this conductor, provided the temperature is maintained constant. So at a given temperature, the Ohm's law, what we call, states that current flowing in a conductor is directly proportional to the potential difference applied across it. Now, taking out the constant, taking out the proportionality and equating it to a constant of proportionality 1 by R, we put this equation like this. And further simplifying, we find V equals IR. Here R is our resistance of the conductor. So from this, we can also say that voltage is nothing but the current flowing in the resistance R. So the product of that gives the potential difference or the voltage drop, which is actually measured by this voltmeter. So there is a current flow and there is a resistance of the conductor here, because of which there is a drop here, which we call it as voltage drop, which is measured by this voltmeter. This is how we measure the voltage. With this, what we have seen so far is about electric current, reason for electric current, the direction of the current, and we also saw what is open circuit and closed circuit, and further we saw Ohm's law. Right, but this resistance is dependent on various factors. Okay. We will see those factors one by one. Okay. First factor, resistor or resistance of a wire or a conductor actually depends on the length of the conductor. It is observed as the length of the conductor increases, the resistance increases or increases with increase in resistance, increase in length. Okay, this is one observation made. The second one is the area of cross section. As the area of cross section of the wire increases, current flow increases. Okay. So as the current flow increases, which means that resistance has to decrease. So we just now saw that current is directly proportional to the applied voltage at a constant temperature, and we saw the relationship V equals IR, okay, through Ohm's law. This means current is V by R. So as the area of cross section increases, which makes more number of charges to flow, the current increases, which means the resistance has to decrease. So the resistance is inversely proportional to the area of cross section. Third factor, we also see that as the temperature increases, resistance increases, which means the current decreases in a given wire at a higher temperature. Another important factor is about the property of the material. So current also depends on the type of material you choose. So there are materials which allow the current to flow freely, and there are materials which oppose the current flow. We have seen that because we have conductors, insulators, and semiconductors, and so on. Therefore, that particular property of the material with which the resistance depends is called a specific resistance, which is nothing but the property of the material that gives rise to resistance. For a copper, the resistivity or specific resistance, symbolically represented like rho, is different from an aluminum material, and that in turn is different from silver and so on. So for a given material, the specific resistance remains constant. So, but having said that, the resistance also depends upon the specific resistance of the wire or the conductor, which is measured in ohm meter. This is the unit of resistance, okay, and specific resistance is measured in ohm meter. So students, so what did we see today? That sums up my part 1, and we will eventually catch up in part 2. So what did we do? We studied what is basically electric current, and we saw what is the reason for electric current, which is nothing but flow of charges, and we saw how the charges were flowing in a wire when excited. And then we also studied about the analogy of current, which is nothing but water flow, which is also current. And we saw an electrical circuit, and open circuit and closed circuit. Eventually, we saw what is Ohm's law, which says that current flowing in a conductor is directly proportional to the applied voltage. And we ended up our discussion with the factors on which the resistance depends upon. With this, I close my part 1 session. See you soon in my part 2 episode.